Welcome all. In this video and sequence of next videos, we are going to explore fundamental theorem of Galois theory, which is most prominent theorem in the advanced field theory due to Galois. Right now we can see one diagram on the screen where I have written the subgroups of automorphism groups of q root 2 root 3 over q and their fixed fields as well. But this particular nature is not just coincidental. We can see here that in particular, if there is a single identity automorphism, it fixes all q root 2 root 3, whereas a complete group fixes q. You can simply see identities contained in identity sigma, identities contained in identity tau, identities contained in identity sigma tau, and all these three subgroups are contained in our group of automorphisms, that is E sigma tau sigma tau. Whereas now you can see reverse diagram that its fixed field is q. Q is contained in q root 3, q is contained in q root 2, q is contained in q root 6, and all these subfields are contained in q root 2 root 3. So it's a reverse inclusion map. Okay, and this particular nature of Galois extension is not coincidental. Fundamental theorem of Galois theory focuses on this fact, and it will explore the idea that this nature is just not that obvious. It is true for any kind of Galois extension. So in this particular video, we are going to start the basic concepts which are essential to understand fundamental theorem of Galois theory. So first of all, we'll start from a definition of character. Definition: character. Character is nothing but a homomorphism from given group G to multiplicative group of field L. Okay, so if G is a group given to you and L is a field provided, then obviously L star is nothing but set of all non-zero elements of L, which is a multiplicative group itself. It is a multiplicative group. So any homomorphism from G, say homomorphism say chi from G into L star is called as character. Is called as character. Okay. Now, what is the definition of linearly independent characters? So, linearly independent characters are nothing but linearly independent functions of G over a given field L. So, definition of linearly independent characters is quite similar with the definition of linearly independent elements, right? But the only fact is that they are functions. So, we can write definition that linearly independent characters. So if a1 chi1 plus a2 chi2 plus so on an chi-n equal to 0, where chi1 chi2 chi-n are characters, okay, and if this implies a1 equal to 0 equal to a2 equal to all these elements an, where all these elements are from L, okay, then we say that these characters are linearly independent characters. Okay, so now we will go into one interesting theorem that distinct characters are linearly independent. Okay, so we are going to talk about theorem that distinct characters of group G with values in L are linearly independent over L. So first of all, let us assume that we have some distinct characters. So we'll prove it here. So let say chi1, chi2, so on chi-n are distinct characters. We want to prove that they are linearly independent. So let's assume that they are dependent. Assume that all these characters chi I are linearly dependent, where one is less equal I is less equal n. Now, since they are linearly dependent, obviously their linear combination is 0, where all these scalars are not 0. Because if linear combination is 0, and all if the linear combination is 0 and all these scalars are 0, that means characters are linearly independent. But if they are linearly dependent, that means some of the constants or some of the values here, a1, a2, dot 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 a n coefficients will be non-zero. Okay, so definitely since we are assuming that chi1, chi2, chi n are linearly dependent, if we assume that its linear combination is 0, not all constants are going to be 0. Some of them will be non-zero. So we are going to assume that a linear combination with minimal number of non-zero coefficients ai. Okay, so let's consider linear combination of chi1, chi2, so on chi n with minimal number with minimal number m of non-zero coefficients. Okay, so m is the least number of non-zero coefficients in the all linear combinations of these characters. Okay, so let me assume that those numbers are non-zero numbers are a1, a2, so on am. Maybe on renumbering, if they are in not in some order, we can reorder them and we can assume that those numbers are a1, a2, dot 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 am. So thus we have expression now. So thus we have a1 chi1 plus a2 chi2 plus so on am chi m equal to 0, where a1 not equal to 0, a2 not equal to 0, so on am not equal to 0. Now what will we do? We will take any element from G. So let G belongs to G. Apply this function on G. So we will find that a1 chi1 of G plus a2 chi2 of G plus so on am chi m of G equals to 0. Right? So let me call this expression as first expression. Okay. Now since all these characters are distinct, definitely there exists some G in G for which image will not equal. So since chi I are distinct, there exists say G naught belongs to G such that chi 1 of G naught is not gonna equal to chi m of G naught. So what we will do, we will, since this expression first expression is true for any G belongs to G, we will replace G by G naught or say G naught G. So what will happen, then we will have this, since chi1 chi2 chi m are homomorphisms, so we can write it as chi1 of G naught chi1 of G plus a2 chi2 of G naught chi2 of G plus so on am chi m of G naught chi m of G equal to 0. Keep in mind that we have replaced G by putting G equal to G replacement as G naught G. So that's why we have this expression now. Now further, what can you do? Now we can multiply the equation number 1 by chi m of g naught, and we can subtract that from equation. Let me call this equation as 2. So we can multiply equation 1 by chi m of g naught, and we can subtract it from 2. That is only to cancel this last term, because here last term is am chi m of g naught and chi m of g. Here we have am chi m of g, so we will just multiply this expression, whole expression, by chi m of g naught, whole expression, right? So, and we'll subtract it from this equation. So what will happen, last term will cancel, okay, definitely, and we will have expression with least number of non-zero coefficients, and that will be contradiction. So let me just prove that what will happen. So after doing this, we will have a1 will be common now, okay, chi1 of g will be common on subtraction, and we will have chi m of g naught minus chi1 of g naught in the first term, right? And plus plus plus, if we continue like this, last term will get cancelled, so we will have second last term, and second last term will be something like this chi m of g naught, as we have multiplied it by chi m of g naught, and minus chi m minus 1 of g naught into a m minus 1 chi m minus 1 of g equal to 0, right? But we can easily find that this particular expression has least number of non-zero coefficients than that of m, okay? So definitely this is going to be contradiction, and this contradiction proves that these characters must be linearly independent, okay? uh, because this g is arbitrary, we can just write it as, if it is not still clear, we can make it clear in this way: a1 chi1, and this chi m of g naught minus chi1 of g naught, plus plus plus, so on, a m minus 1, then chi m of g naught minus chi m minus 1 of g naught, okay, into chi m minus 1 of g equal to 0. So this expression is going to be 0, right? So a1 chi1 chi m of g naught minus chi1 of g naught, plus plus plus, so on, a m minus 1 chi m of g naught minus chi m minus 1 of g naught, okay, into chi m minus 1 equals to 0, because g is arbitrary, right? So g is any random element of g, so this function is going to be 0, and this shows that a1 is constant, g naught is fixed, so that's why chi m of g naught minus chi1 of g naught is a fixed number. So definitely this linear combination asserts that we have less number of non-zero coefficients than that of m, so this is contradiction, right? And it proves that all the characters must be, distinct characters must be linearly independent. We can use this idea to establish one note that since all the distinct characters are linearly independent and character is nothing but homomorphism, okay, so we can say that if say sigma 1, sigma 2, so on sigma n, okay, are distinct embeddings. Embeddings means injective homomorphisms. Distinct embeddings of field k into L, then they are linearly independent, okay. In particular, we can say that distinct automorphisms of k are linearly independent. So in particular, distinct automorphisms of k are linearly independent, okay. So with this, I stop here. In the next lecture, we will talk about that subgroup of automorphisms and its fixed field have some common point, that the number of elements in subgroup of automorphisms is exactly same with the degree of extension of k over its fixed field. Okay, so that result will be established in the next session. Stay tuned. Thank you.